All right, thank you very much. Thank you for inviting me to my first PCC meeting. So as I mentioned previously, I'm a postdoc at Los Alamos National Lab working on impact cratering and space debris processes. And we've been working extensively with the Artemis 2 science team and also some folks from the Apollo science team on studying real-time cratering via impact flashes and impact loops. And I should really just emphasize it's got my name on the slide, but that's because the list of co-authors in this work is now about 50 people long. And so I had a choice between putting all of them on there or just putting myself. And I figured for the sake of neatness, I would just put myself on there, but there are many others who contributed to and helped out with this work in one way or another. So obviously in this room, we thought a lot about why we should study craters at all. I don't think I need to put in my why craters are important slide, but perhaps one thing that we don't think about so often is why is studying craters in a sort of time-resolved manner interesting? So rather than thinking about lunar cratering on a 100 million to billion year timescale, why should we be thinking about studying craters on a millisecond to second timescale? And there's a few reasons for that, some of which are quite obvious and some of which are possibly not so obvious. But the first is, of course, that we can start to get at the size frequency distribution of impactors in a time-resolved way. So many of the models we have for surface ages or surface dating, understanding volatile emplacement, they make some assumption about how constant the impact rate has been over some length of time. If we're studying impact processes in close to real time, we can look at the variability, and there's variability in the impact rate we know on a few different scales. For example, on the moon, there's obviously monthly periodicity. There's an annual periodicity due to intersection with various meteoroid streams, but there's almost certainly longer periodicities as well associated with, say, resonances in the asteroid belt of Mars or interactions with the giant planets. And so if we're looking at impacts in a time-resolved manner, we can start to get at how much that variability might affect our estimations of how the average cratering rate has changed over time. The second thing is we can start to get at real-time impact dynamics. So we obviously have all these questions about exactly how these crater processes form, what are the transients and how long do they last? Well, if we're doing things like measuring an impact flash and we're taking an image every millisecond or every 10 milliseconds, we can actually start to unlock some of the information about how those transients are behaving in real time with observations that we can then look at with a pretty good constraint on. The next is as a seismic source constraint. So we're unfortunately in a bit of a lull at the moment. We have no functioning seismometers anywhere else in the solar system, but we will get back to a point, hopefully in a few years with US stuff. And China's Chang'e 7 launch goes well in a few weeks. They will have a seismometer on the moon. All of these impact flashes act as seismic sources. They contribute to the microseismic hum. Even here in Flagstaff, the majority of the microseismic hum comes from the ocean. We're a long way from the ocean, but it's a global noise background. On the moon, the global noise background comes from micrometeoroid impacts. And occasionally one is big enough that it will act as a seismic source that can be detected anywhere on the entirety of the moon. And if we can see that flash in real time, that removes a lot of degeneracy from our inversions for internal structure or for studying, the source mechanisms of moonquakes, because we can tell you exactly where on the moon and what time to the nearest hundredth of a second the energy was actually released. And then, of course, finally, and this is one that it's clearly going to become more relevant in the Artemis era, these impact events pose a direct and an indirect hazard to astronauts' infrastructure on the surface. And let's be fair, the direct hazard, i.e. the likelihood of you being hit by a meteoroid if you're sitting on the surface of the moon, is pretty small. The likelihood of you having some adverse interaction with dust or ejecta or seismic waves from an impact is probably a bit higher. But actually, one thing that we're going to touch on at the end, when it comes to artificial impacts, these rates are going to go up massively. And we're now at an era where we have to start worrying about space debris impacts on the moon as well. And so it might seem like an odd thing to even consider the risk of an asteroid being hit by a meteoroid. But unfortunately, in the modern era that we live in, this risk is actually becoming very real. And so I just want to sort of give a shout out to where I started my kind of impact cratering career, which was working on the InSight mission, so looking at real-time cratering on Mars. I was very lucky to co-chair the impacts working group with Ingrid Dauboff from Brown, who I'm sure many of you will know. And we spent a lot of time looking at all these questions on Mars. We obviously don't get impact flash measurements on Mars, but we do very often see the resultant craters, the blast zones, helps that we have an atmosphere. we can see those in the hours after they formed at the highest scales of craters. And so there's a lot of questions that we were able to answer about the internal structure of Mars by using these impacts as seismic sources. And there are lots of questions still to be answered about things to do with seasonality of impacts. And I'm not going to talk anymore about seasonality on Mars of impact events, but I wanted to put this plot up here because I know we have some statisticians in the room who are very good at making the most of small data sets. I've started spending some time thinking about why do these seismically detected impact events, which are the red dots, sort of occur in such a weird way. So the VF events, the blue crosses, those are other events. They may or may not be impacts. But there are so many weird things about this distribution, right? So it's a spiral plot. Each loop of the circle is Martian year. And it's sort of, you can see the seasons from L sub S0 all the way around. Why are there so many more events in the second year than the first year? Why do those impact events seem to cluster between L sub S90 and 130? Those are not things we expected would happen. In fact, we predicted quite the opposite. Are those two sets of distributions compatible with each other statistically? There's all sorts of interesting questions that we can start to get at when we're looking at cratering, where we can give you timing down to the second or the minute that we simply cannot answer by looking at surfaces that have been saturated in craters for billions of years. So just to talk briefly about what are these observables that we're looking at. There are three things that happen when an impact occurs on an airless body. One is you get a flash of light. Two, you get a plume of ejecta. Sometimes there's also vapor in there, depends a little bit on the dynamics. And three, you obviously get a new crater as well. On Earth and Mars, you get a sonic boom in the atmosphere, which is brilliant. We can use that to track and localize things very well. Clearly, that's not relevant for the Moon and therefore not relevant for Artemis or Apollo. So this is a video from the Meteoroid office at NASA's Marshall Space Flight Center. And just in case you didn't catch that, let's play it again. If you look in the lower right corner, you're going to see a little flash of light. And this is one of the brightest impact flashes ever detected. I think it's around magnitude +3. And it lasts a fraction of a second. So it's probably associated with something that is in roughly the kilogram size range, going at several tens of kilometers per second, instantly being vaporized. This particular event, they actually managed to get a follow-up image with LRA of the resultant crater, which is great as well, right? Because then we can start to compare how accurately we measure the location from Earth, where we've got an atmosphere in the way, to the location that actually occurred. We can use that to calibrate other measurements we make of impact flashes. It just reduces a lot of the degeneracies here, where we can do this observation from the ground of the flash and then from lunar orbit, the resultant crater of the fact. And these programs are great. They've kind of come and gone over the years in terms of how well they're funded and how much time they get. We can clearly really only look realistically at flashes on the darkened side of the Moon, and we realistically need to be in astronomical twilight here on Earth to do it. People are pushing that from both ends to try and look for the big stuff on the lit hemisphere, or indeed to look during Earth's daylight. But there's programs at NASA Marshall. There's a big program in Greece, and there will be a new program ran out of IPGP in Paris. The trouble is that those all have limited times. They have cloud cover restrictions. They have weather restrictions. They have restrictions to do with the phase of the Moon. And so one thing that we're trying to do as well is push this out as far as possible to get smaller telescopes, amateur telescopes, to do flash monitoring as well. So how did this sort of all come together? Some of you are probably on the Lunar L mailing list that's maintained lovingly by Clive Neal at Notre Dame. And so we sort of were chatting about Apollo on this mailing list. And one day we get an email from Jack Schmidt, who I'm sure many of you will have met previously, who goes, just in case anyone's interested, like, oh, we made, I saw an impact flash on the Moon. It's like, okay, well, wow. You don't often get to see that. He was like, yeah, we were orbiting the Moon, and I looked out the window and I saw an impact flash, and it was very different to a cosmic ray, so I'm pretty sure it was an impact flash. And I wrote back and was like, hey, fellow New Mexican, did anyone check the seismic data? And he was like, no, I don't think so. So then, I wrote to Yosu Nakamura, and these two are both alive. They're in their mid-90s now, still doing science though. And I said, hey, Yosu, did anyone check the seismic data when Jack reported his impact flash? And he was like, no, I don't think so. And this guy, like, he still has the paper records, if you've not met him, from the original Apollo printout. So he knows everything. He said it wasn't looked at, it probably wasn't looked at. So we thought in the run-up to Artemis, why don't we look at the seismic data from Apollo as well? Because that seismic data, as I mentioned previously with InSight, that's giving us insight into the real-time processes. So there were 3 impact flashes that we actually managed to find by digging back through the Apollo transcripts. 1 on Apollo 16, 2 on Apollo 17. There's a fair question to be asked. Why did they not see them on Apollo 13? They didn't really have much else to do on the dark side of the dark inside of the moon. It was pretty cold, and there weren't many lights on at the time. So why did they not see more impact flashes? And that's a question that we don't have a good answer to. It's perhaps telling that the lunar geologists saw 1/3 of all the impact flashes seen. But hey, there you go. They said, obviously we only have the astronauts' word for them. The Apollo capsule did not have continuously recording exterior cameras the same way Artemis did. They said that the impact flashes they saw were very distinct from cosmic ray flashes, so we can only take their word for that. Oh, that was meant to be bigger there as well. And so, yeah, there were 3 flashes that were recorded on 16th and 17th. So Jack saw his flash in Grimaldi crater, which is visible from Earth quite nicely. Ron Evans saw a flash in Mare Orientalis, and that's really right on the edge of what you could ever see from Earth. And then there was the 3rd flash on Apollo 17, which was somewhere over the horizon. So they didn't actually see where on the surface it was localized to. But we have 2 approximate flash locations, and there are 4 reasonably functioning Apollo seismometers on the surface, which we can cross-check those readings against. And so what we did is we basically went back and hunted through all the Apollo data to look for events that matched in timing. And so we know there are lots of different kinds of moonquakes. There are impact moonquakes, thermal moonquakes, deep moonquakes, and as many glitches and types of glitches as you can possibly imagine in the seismic systems on Apollo. But we went back through and we found a few events that looked a little bit promising. But unfortunately, we weren't able to find any that were a concrete match. And so what we do is we know the time that those events were recorded on the seismometer. We have an approximate time that the astronauts reported the flashes. And so we can run a seismic model that basically propagates a seismic pressure wave through the interior of some structure of the moon that we give it to try and see if that energy was detected at the seismometer. And it suggests that for these 3 events, unfortunately, none of it was. But it's a really good pipeline for how we're going to be able to do this once we have Artemis astronauts observing from orbit, and we have future NASA seismometers or other country seismometers on the surface recording data. Of course, we can now do what they couldn't do in the Apollo era. We can run full waveform seismic models that propagate energy from craters, fresh craters being formed through the interior of the moon, through a strongly scattering layer. So not only can we try and match the arrival times for these flashes that will be seen by Artemis astronauts, we can actually try and match the waveforms as well. And if we match those waveforms, we can start to figure out how the energy was released during the cratering process, which ideally we should be able to compare also to our models and then also to the sort of light curve of those craters forming if we manage to resolve them. So the next thing, of course, is Artemis 2. So Artemis 2 happened in April of this year. It was pretty cool. It was a very busy few weeks because we had this project and then we had to go out on a boat in the Pacific Ocean to record the sonic booms to use as space debris calibration. So it was all a bit chaotic, but one of the objectives of the science sort of part of Artemis 2 was to look for impact flashes on the lunar surface. So you may have seen that there are a bunch of news stories about the astronauts reporting 6 flashes on the lunar surface, which they felt, again, were quite distinct from the cosmic ray flashes that they also saw. Just as a little side note, everyone's favorite Harvard astronomer obviously managed to find a way to link it to aliens immediately. But these impact flashes were really interesting, right? Because we had these 6 flashes now, and unlike on Apollo, this was one of the only real science objectives of Artemis 2 was to look for these impact flashes. It's one of the things that, in theory, a human eye is potentially better at than some of the tools that we have that are automated. And so we had these 6 flashes, and the question was how does that compare to the expectation rate for flashes in lunar orbit? And it turns out that's something which really hadn't been looked at in any great detail. We have very good measurements of how many flashes you see on the moon's darkened hemisphere from Earth. It turns out you see about 10 flashes per hour of magnitude 12 or greater. So clearly at the lower end, you need a telescope to see them. But that rate is pretty well constrained. There are other complications that happen when you're in a close lunar orbit or indeed a close lunar flyby like the Artemis astronauts were. And you know, the flash observation rate is dependent on two things. One is the impact rate, which is probably somewhat similar to on Earth, but of course you have to adjust for the fact that you're looking with your eye, which is far less sensitive than the most sensitive CCDs that we have. And of course you have this complication of the flyby altitude being continuously changing. That changes the illumination geometry. It also changes the brightness of the flash, right? So if you're looking from Earth versus looking from 5,000 kilometers above the moon, a flash is about 12 to 15 orders of magnitude brighter. So, you know, at the altitude that the Apollo astronauts were at, the brightest flashes would have been actually probably painful to look at. But that, you know, that needs to be modeled and accounted for as well. You know, the distance to the horizon is obviously going to matter as well, and what proportion of that horizon is in light versus in darkness. We've assumed in these sorts of models that the impact process is Poissonian. That's probably true on a large enough scale and a small enough scale, but there's some scales in the middle where maybe that isn't true exactly. And you know, we didn't have an exact trajectory for Artemis at the time, so we go, okay, we'll put them on a hyperbolic trajectory with the closest point of about 4,000 kilometers above the point along the Earth-Moon line, but on the far side. And so, yeah, how does that vary? So the first thing is, you know, what fraction of the horizon is visible from Artemis, or, you know, Artemis 2 or a future Artemis mission on a flyby or an orbit? And this was actually a little bit surprising to me because I didn't really have any intuition for how the horizon distance changes when you're in an altitude of 1,000 kilometers. So at the point of closest approach to the moon, Artemis 2 was actually still pretty far away. So they could probably see about 35 to 40% of the entire lunar surface. And fortuitously for us, you may recall they actually saw a total solar eclipse at that time. So that means that the side of the moon that they were looking at was in complete darkness. You know, the next question is, of course, let's assume that impact rate of about 10 flashes per hour of magnitude 12 or greater. How does that translate into the number of flashes that you would expect at different flyby heights? Because you've got that horizon moving up and down. And of course, that flyby height controls the change in magnitude. So these are four curves of time in hours, probability of more than one flash, more than or equal to one flash, for 5 different flyby altitudes from 100 kilometers to 10,000 kilometers. And in brackets, you can see the change in magnitude that you get as well. So, you know, Apollo on the order of 100 kilometer flyby altitude, you actually have to wait a pretty long time to get a 50% chance of seeing an impact flash on Apollo because it was in such a low lunar orbit. It's about 3 and a bit hours. And you know, as I said, you know, it would a flash that was magnitude 5 from Earth would be about magnitude 12 from Apollo, so minus 12 from Apollo, so it would be bright. Conversely, if you're at sort of between 5 and 10,000 kilometers, that's the orange and the yellow curves, you'll see that the probability of seeing one or more flashes basically saturates after about an hour and 15 minutes in that you're almost certain to have seen one. And that's just because you're so much higher up that you can see the whole lunar surface. And also, interestingly, the difference in flash brightness is about 8 orders of stellar magnitude for the Artemis altitude. Things that are about magnitude 12, which is the detection limit for telescopes on Earth, therefore become about magnitude 3 to 4. Magnitude 3 to 4 is a reasonable estimate of what your eye can see under ideal conditions for something that isn't transient. So, you know, you can see down to magnitude 5 or 6 in good conditions if it's a static source, but if it's a transitory source, magnitude 3 to 4 is actually a pretty good threshold. So that makes the math much easier. Basically, anything that you could see with a telescope on Earth, in theory, the Artemis astronauts could see as well. So, of course, the next question is, we can say a statement like that. So the probability of more than 0 flashes is more than 90% after an hour for Artemis astronauts. How variable is that? So we can, we can put it together as a sort of Monte Carlo style model, if you want, right? Let's take that flash distribution and just generate a Poisson curve for all of those flashes at these various time intervals. And then we can look at how variable that rate is. And of course, this isn't actually giving you any more information than the other curves. It's just multiplying things together. But I think it's perhaps a more intuitive way of understanding what the variance is in that Poissonian distribution than you get from just looking at curves. So you'll see this line isn't flat, right? It's not that there's a uniform probability of seeing impacts across all time. And that's because we have that phenomenon that we noticed earlier, where as you get closer to the lunar surface, you see less of the horizon. So you will see that curve start to flatten out in the middle. Now, we made these curves before we knew what date Artemis was launching, so we couldn't actually account for the fact that at some point they were going to fly into sunlight, and they wouldn't be able to see anything, basically. So this, at the moment, is assuming they were in darkness the whole time, which is probably okay, actually, in the middle, but not so true at the edges. And you can see, if you take a sort of 1 hour chunk in there between 0 and 1 hour, the slope of that line, it covers about 4 or 5 flashes. So what that's suggesting to us is this very sort of back of the envelope model. Seeing 6 impact flashes over a few hours is not unexpected. That's commensurate with the impact rate that we expect, which was an obvious question, right? Because people say, well, okay, Apollo spent, I don't know, in total, probably 700-800 hours orbiting the moon, right? Sometimes it was just a command module pilot. They only saw 3. Well, actually, that's just a feature of the fact that Artemis was so much higher over the surface when it did its flyby. The next thing we can do is obviously pretty trivial to just see, well, what happens if we put an arbitrary daylight boundary in there? And you'll see the flash rate stabilizes, so we can, at some point, I will figure out how to get the spice kernels out and the pointing and figure out how much time they were actually in sunlight, and then we can actually do this for real. And the other thing that we can start to do is, what if we have a time variable right in there? So there was one of the Artemis launch windows at the end of April, they would have probably actually flown into a meteor stream impacting the moon. Pretty low risk stuff to them, but it would probably increase the number of flashes that you see quite significantly. And that was observed in Apollo data from seismic stuff, and it's possible that with future Artemis missions, we'll see it in the visual data as well. I'd just like to give a shout out to one of our astronomers, Jörg Tomaszek from Germany. Unfortunately, the impact the launch window that Artemis chose in the end was very unfavorable for observations from Earth. The moon was about 70% illuminated, which basically means there's so much stray light, unless you have a really, really fancy telescope set up, it will just bleed all the way across the sensor. We did pick out one candidate flash. If I'm brutally honest, if this had happened on any other night, I would have just said it's probably a cosmic ray, let's move on. But the fact that it lines up in timing, you hopefully can see it in there, it lines up in timing and maybe in rough location of where the astronauts were looking at the time. That's interesting. I say rough location because NASA still hasn't released where or when the astronauts saw the flashes. They were, coming around the edge of the moon, so some of them happened in radio blackout. I don't know why that hasn't been released, but when that information is eventually released, that is a candidate flash that we have a timing and location for. So I just wanted to touch briefly on something it's a little bit more controversial, but is relevant, and as I said, is very much a topic of ongoing collaboration that folks might be interested in. Unfortunately, I said that I worked on space debris and I worked on impact processes. Well, those two things tend to actually not go together as much as you would imagine, because most space debris does not reach the surface of the Earth, thankfully. SpaceX likes to launch things into space, and as you may have noticed if you look up the night sky recently, they're a little bit less fussed about where the stuff ends up after the fact. And so it turns out that one of their Falcon 9 upper stages is actually going to impact the near side of the moon. And so this is something that is way bigger than your average impact flash meteoroid, right? This is about 4 tons of metal. Probably has some fuel in there as well, which will likely explode on impact. And at about 2 o'clock in the morning Eastern time, it's about 7 a.m. UTC on August 5th, it's going to impact right on the lunar limb. And that's really interesting, right? It's going to be on the bright lit side of the moon, which is slightly problematic, but it is so close to the limb. This is very fortuitous. If the plume from this impact climbs more than about 800 meters above the surface, it will end up being silhouetted against space instead of silhouetted against the moon. So this is potentially a sort of chance to test all of our most sensitive crater formation flash prediction models against a known event where we know when and where it's going to happen, meaning that we can point some pretty hefty assets at it. So the Very Large Telescope will be looking with an 8.5-meter telescope at this event. We were hoping we get Hubble to look at it. Unfortunately, Hubble is no longer in a fit state to point at the moon. And JWST obviously cannot ever point at the moon. But we will have assets across the US looking at this, amateurs from California all the way out to Europe who are going to try and do that. So if you know anyone or you have an observatory at your institution, encourage them to do this. It's like an hour of their time, but potentially very valuable. So we're expecting an impact flash. It's actually a relatively slow impact. It's funny, I say it's about 2.5 kilometers per second. That's so slow. And then all the rocket people turn around and they're like, that's so fast. And all the creative people turn around and they're like, that's really slow. So it's going to be very slow, which probably means the flash of light will, I would guess, last on the order of a second. It's slow enough that I suspect that the impactor is going to get decapitated as well. So it will probably break as it impacts the surface, and I wouldn't be surprised if we get an extended crater chain or a double impact or something. The impact plume, it's going to be real. It is really tough to model that. I'll show you some nonlinear shock physics modeling in a minute. But we have some interesting predictions for that plume, and then the fresh crater. And that crater will be observed by LRO. Unfortunately, their orbits are basically orthogonal to the impact direction, so there's not much they can do in real time. But fortunately or unfortunately, the Korean Pathfinder lunar orbiter, they're going to go through a conjunction of a few kilometers with the SpaceX rocket before impact. And the uncertainty on the ephemeris is a few kilometers. So they're trying to figure out how to avoid it without knowing exactly where it's going to be, which is a great thing for them. But it does mean they'll get basically close to real-time observations for this event. We've done some shock physics modeling using HOS, which is the code from Los Alamos. We're projecting about 1,100 tons of material will be excavated by this event. Obviously, most of that will fall straight back onto the surface. It will be in that transient ejector curtain. But if we look at the ejector velocity distribution, we've kind of got this to the -3 scaling law, power scaling law in there. Vast majority of the stuff is very slow, but the fastest moving stuff is going to be up at hundreds to 1,000 meters per second. So that gives it a downrange ballistic range of about 1,000 kilometers and a maximal altitude of the stuff we can resolve in this model of about 1.5 kilometers. The stuff we can't resolve will probably go, I would guess, to about 5 kilometers. We've done some modeling the particle trajectories as well, which is helping to inform the impact hazard, because this stuff is going to keep happening more and more with more missions going to the moon and more people on the surface. And we can also look at the maximum altitude. So it may surprise you, but some of these impacts could potentially launch small particles into orbit in such a way that is actually problematic for orbit spacecraft. So that is all I wanted to say today. I've put a couple of resources up that might be of interest, the Apollo Flash paper, and then also the Impact Flash paper, which is a citizen science project that I'm running with the NASA headquarters office. Anyone is welcome to contribute to that. And obviously, if you have professional observations or observatories available that would like to contribute to the Falcon 9 event or any of our other Impact Flash monitoring projects to look at real-time cratering, you're more than welcome to get in touch as well. Thank you.
Probably one question. Go ahead.
You said you're using HOS, right?
Yes.
Okay. I figured. What strength model of material models you're using?
Yes, I think they used it's not Tillotson, it's the other one. Is there a Hulls, the one that they got out of a Hull sample thing?
I'm not sure. I know they have Tillotson.
Yeah, don't think they used the Tillotson one for this one. It was done by the people who do the fancy explosion stuff. So I'm sure they know what they're doing.
Did they use Drucker-Prager for strength?
I don't think so, actually, but I don't. Yeah.
Maybe another question. Yes, okay. You speak about the sorry. The number of impact per hour, and do you think about astronauts? They have a specific tool to help them guard against this.
Yeah, great question. The trouble is the stuff is coming in so fast and it's so small. There are a few risks that I think are worth being aware of. One is that if you're doing something very sensitive and you see a flash of light near the astronauts, if that plume has fines which are traveling tens to hundreds of kilometers, it actually might be worth thinking about a warning system for that. Clearly, for most stuff, this stuff is, the ejector's going fast. It'll put a ding in the side of your spacecraft, but it's probably not going to go through a person. If you're doing something much more sensitive, though, where you really need to keep the dust out, it probably is a hazard that you could and should guard